Okay, so on now to ionic bonds. Remember that ions are atoms or molecules with electric charge, and that oppositely charged ions attract one another. Anything with a positive charge and a negative charge attract to each other. And when this happens, when we have resulting attraction, that is called an ionic bond. Ions that form ionic bonds together usually pack into tightly clustered lattices in something called an ionic compound. So you can have singular molecules with an ionic bond, but usually these are packed together, again in a lattice, to form a large lattice structure in a crystal. Now, these ionic compounds have high melting points and are usually soluble in polar solvents. Why does this make sense? High melting point because if you think about it, these are all packed next to each other very tightly. And for something to melt, it has to separate, right? To melt, we have to go from a solid to a liquid, which means we have to separate off. And if you are very tightly packed with ionic bonds, that means they are very strongly connected and it is hard to separate off from a solid to a liquid. That means that you have a high melting point. It's going to take a lot of energy to separate these bonds. Now, why is it soluble in a polar solvent? Well, remember, if each bond is made up of charges next to each other, and if you have something that is polar, it also has charges. So let's use water as an example here. Here's our water. Water has a polarity in which one end is more negative, one end is more positive. So that means that these polar ends will be attracted to the ionic elements within, and they're able to pull them off easily via this attraction. Okay. One can imagine generally that ionic bonds arise from the transfer of an electron from a metal to a non-metal. Usually this is the case, from a metal to a non-metal. In an example here, we can talk about gaseous sodium. So think about sodium. Sodium is it a metal or a non-metal? Think about that. It can transfer an electron to gaseous chlorine. In this case, the sodium here loses an electron, so it becomes positive, and chlorine gains an electron, so it becomes negative. The process of this happening, of the losing and gaining of an electron, is endothermic. It takes heat to do this, but when you form the solid, when you form the ionic bond that ultimately happens, as shown below, between sodium and chlorine to form sodium chloride, it is an exothermic reaction. So this spontaneously happens even though the first process is endothermic. The formation of the solid is so strongly exothermic that it drives this reaction. Now, normally we talk about ionic bonding between things like sodium and chlorine. However, in organic chemistry, we're going to focus a lot on carbon. This is usually called the chemistry of carbon. And carbon atoms rarely form ions. They don't usually completely give away electrons. Hence, ionic bonds are pretty rare in organic chemistry, you'll see. Instead, we'll be talking mostly about covalent bonds. Covalent bonds are going to hold together all of the organic molecules we'll talk about. And this involves sharing of electrons between nonmetal atoms. So it's just nonmetal atoms with other nonmetal atoms that are sharing electrons. This is more common. Ionic bonds do appear, however, when we make salts of things with carbon, nitrogen, oxygen, and hydrogen, which are nucleophilic. That means they're electron donating. And they will form the salt with a non-metal atom. So we will occasionally see this. So at the bottom here, you can see this whole molecule is an organic molecule. It's made of covalent bonds. However, it does have a formal negative charge. And because of this charge, the whole molecule itself can form a salt with a metal atom, sodium. Usually, as I said above, the organic molecule will be nucleophilic, meaning it will be the one donating electrons. It will have the negative charge, and it will be forming with a salt that is positive: sodium, lithium, potassium, etc.